study of the planets, moon and stars beyond our Earth has been going on for thousands of years. The exploration of space only began about 50 years ago. In October 1957, Russia sent an unmanned spaceship named Sputnik into orbit around the Earth. Since then, space missions have been sent to many planets, moons, comets and asteroids. In this video, we will look at how maths is being used in the exploration of our solar system. A lot of questions will be asked, but not many of them will be answered. Hopefully, you'll find some answers in your math class. One current space mission is NASA's Messenger mission to the planet Mercury. The craft left Earth in August 2004 and will start orbiting Mercury in March 2011. Unlike the huge rockets that launch the craft into space beyond Earth's gravitational pull, the Messenger craft is about the size of a four-wheel drive. Another current mission is NASA's New Horizons mission to Pluto, and beyond to the Kuiper Belt. This craft left Earth in January 2006 and will reach Pluto in July 2015. The New Horizons spacecraft is only about the size of a piano. Much of our knowledge of the motion of planets is due to famous scientists such as
Galileo Figaro,
Kepler and Newton, who developed mathematical models and formulas for things like the force of attraction between large objects, the time it takes for a planet to orbit the Sun, the minimum speed required for a rocket to escape the gravitational pull of a planet. Scientists involved in space missions make lots of calculations which use algebra, such as how gravitational forces change as spacecraft gets further from Earth but closer to other planets. The spacecraft heading to Pluto is currently moving so fast that it travels 1 million miles each day. How can speed like this be converted to kilometers per day? And how does this speed compare with the speed of a jet or a very fast train? We know how we refer to positions in a theatre, or in a map, or on the number plane. But what about on Mercury or Pluto? When spacecraft takes pictures of these planets, how do NASA scientists relate the position of one image compared with another? And how do they keep track of the position of the spacecrafts which are moving in 3 dimensions, while the planet around them are also moving? Knowing about circles and spheres is important in astronomy, because the planets are shaped like spheres and they move in circular orbits. For example, if we know the distance from Earth to the Sun, we can use c equals 2 pi r to calculate the length of Earth's circular orbit and its speed of travel. But if we know that the diameter of Mars is about half that of Earth, does that mean that the surface area of Mars is only half as big as Earth's? And what about the ratio of their volume? And if all the planets are moving around the Sun in a circular orbit, at different speeds. How do scientists calculate the best path for spacecraft to take from Earth to Mercury? Scientists involved with these space missions often make calculations involving very large numbers, like the mass of a planet, and very small numbers, like the wavelength of light. How do they make these calculations without running out of space on their page? Calculations involving angles are essential for working out distances, speeds, and forces in space. One example is apparent diameter. A full moon, for example, has an apparent diameter of half a degree or 30 minutes of arc. The apparent diameter of the planets vary because their distance from the Earth varies. How accurate are scientists' calculations? For example, what accuracy is lost when we take into account that the Earth isn't exactly spherical, or that planets move in elliptical paths around the Sun rather than perfectly circular orbits? Is there some way to estimate the size of errors? And how can we justify the degree of accuracy of results? Can we make calculations more accurate, perhaps by using a better method? In your math classes this semester, you'll hopefully come up with answers to some of these questions raised in this video.